Time does not slow down near a black hole. Time stops, not metaphorically. Not as a figure of speech borrowed from poetry or philosophy, literally, measurably, verifiably. The flow of time itself, the same time that governs every heartbeat, every orbit, every signal ever transmitted across the universe, grinds toward absolute zero the closer you approach the edge of a black hole. This is not speculation. It is one of the most rigorously tested predictions in the entire history of physics, and every experiment humanity has ever conducted to challenge it has only confirmed it with greater precision. The universe contains objects so dense, so gravitationally extreme, that they do not merely warp space. They warp the very fabric of time itself. They bend the dimension in which cause follows effect, in which the past stays behind and the future lies ahead. Approach one of these objects closely enough, and the arrow of time, that invisible, inexorable current that carries the universe forward, begins to point sideways, then backward, then nowhere at all. That is not science fiction. That is general relativity. That is Einstein and Penrose and Hawking and a century of observational astronomy converging on a single staggering conclusion. Black holes are not just objects in space. They are ruptures in the structure of reality itself. The question has haunted physicists for more than 100 years. What actually happens when something, anything, crosses the point of no return at the edge of a black hole? What does the universe look like from inside an object that has, by every measurable standard, severed its relationship with the rest of existence? Is there an inside at all? And if time stops at the boundary, then what does it mean for something to exist beyond it? These are not rhetorical provocations. They are open, active questions sitting at the absolute frontier of modern theoretical physics. And the answers, as far as science has been able to determine them, are stranger than almost anything the human mind has ever attempted to process. To understand why, you have to start where the story always starts, not with the exotic, not with the extreme, but with the utterly ordinary. Gravity is the weakest force in nature, by an almost incomprehensible margin. The electromagnetic force that holds the electrons in an atom to its nucleus is roughly 10 to the power of 36 times stronger than gravity. That is a 1 followed by 36 zeros. A small magnet stuck to a refrigerator door is defeating the gravitational pull of an entire planet. Every time you pick up a pen from a table, the muscles in your fingers are effortlessly overpowering the gravitational attraction of 6 trillion kilograms of rock and iron beneath your feet. And yet, gravity is the force that rules the universe at the largest scales. Not because it is strong, but because it is cumulative and inescapable. Every atom of matter in existence exerts a gravitational pull on every other atom of matter in existence, across any distance, with no upper limit and no shield. You cannot build a gravitational insulator. There is no material, no field, no known physical process that blocks gravity. It reaches everywhere, always, forever. And when enough matter piles up in one place, when the cumulative gravitational attraction of millions, then billions, then trillions of solar masses of material becomes so intense that not even the internal pressure of atoms themselves can resist it, gravity wins, completely. The result is a singularity, a point, or more precisely, a mathematical limit, at which density becomes formally infinite, at which the known laws of physics break down, at which every equation physicists have ever written either returns an undefined result or simply ceases to describe anything coherent. The singularity at the center of a black hole is not merely a very dense object. It is the place where our current understanding of reality reaches its hard boundary and goes no further. Surrounding that singularity is the event horizon, and this is where the misunderstanding almost always begins. Most people, when they try to picture a black hole, imagine something like a cosmic drain, a visible funnel or void in space, actively pulling everything nearby into a dark center, with a clear and definite edge that you could see approaching. This picture, though visually intuitive, is wrong in almost every important detail. The event horizon is not a physical surface. There is no wall, no membrane, no detectable barrier of any kind at the boundary itself. It is a mathematical threshold defined entirely by the geometry of spacetime, the point at which the curvature of space and the distortion of time have become so extreme that the escape velocity required to leave the region exceeds the speed of light. Since nothing in the universe can travel faster than light, approximately 300,000 kilometers per second in vacuum, nothing that crosses the event horizon can ever return. Not matter, not radiation, not information, not causality itself. Think about what that means in terms of scale. The event horizon of a stellar mass black hole, the kind formed when a star roughly 20 or 30 times the mass of our sun collapses at the end of its life, has a radius of roughly 60 to 90 kilometers. That is smaller than many cities on Earth. The entire gravitational catastrophe, the entire machinery of space-time rupture, fits within a sphere that a commercial aircraft could fly across in a matter of minutes. From the outside, you would see nothing at the boundary itself. The horror, if you can call it that, is invisible. For a supermassive black hole, the kind that anchors the centers of most large galaxies, the numbers become something the human brain struggles to accommodate. The black hole at the center of our own galaxy, known as Sagittarius AI, has a mass of approximately 4 million times that of our Sun. Its event horizon, the Schwarzschild radius, is roughly 12 million kilometers across. To put that in terms that register as something other than an abstraction, the distance from Earth to the Moon is about 384,000 kilometers. The event horizon of Sagittarius AI has a diameter roughly 31 times that distance. It is not a point. It is a sphere of absolute no return larger than most people's intuition can genuinely process. And M87 the black hole in the center of Messier 87, the one that humanity photographed for the first time in April 2019 using the Event Horizon Telescope, a planet-spanning array of synchronized radio observatories, is in a different category entirely. Its mass is approximately 6.5 billion solar masses. Its event horizon has a diameter of approximately 38 billion kilometers. Our entire solar system, from the Sun to the outermost edge of the Kuiper Belt, spans roughly 9 billion kilometers. The event horizon of M87 Kau would swallow our solar system 4 times over and still have room. That photograph, a fuzzy, orange-tinted ring of superheated plasma glowing against the silhouette of an object from which no light escapes, was not a computer simulation. It was not an artist's rendering. It was a direct observation. Photons of real light, emitted by real gas orbiting at a significant fraction of the speed of light, bent by space-time curvature of a magnitude that no other object in the known universe can produce, captured by radio telescopes on 4 continents working in perfect synchrony, reconstructed into a single coherent image by algorithms running on hundreds of processors. It was the moment the black hole stopped being a theoretical prediction and became an observed, documented feature of the observable universe. The physics behind that image, and behind everything that the image implies, reaches back to a single document published in November of 1915. That document, a set of field equations written by Albert Einstein and submitted to the Prussian Academy of Sciences, did not merely describe gravity as a force between masses. It redefined gravity as the curvature of spacetime itself, as the geometric consequence of mass and energy bending the 4-dimensional fabric of the universe. And embedded within those equations, almost immediately apparent to anyone who worked through them, was a prediction so extreme that Einstein himself initially refused to believe it was real. Under the right conditions, spacetime could curve so severely that it would create a region from which nothing, not even time, could escape. That prediction is what we are here to examine. Not the black hole as an object, but the black hole as an event in time, or rather, as the place where time itself runs out. The deepest mystery is not what falls in, it is what happens to time when it does. Karl Schwarzschild was solving Einstein's field equations from the Eastern Front. It was the winter of 1915, and Schwarzschild was stationed as an artillery officer in the German Imperial Army near the Russian front lines. Amid the cold and the chaos of one of history's most destructive wars, he found Einstein's newly published general theory of relativity and did something extraordinary. He solved it. Exactly. Completely. Within weeks of publication, Schwarzschild produced the first exact solution to Einstein's field equations, describing the geometry of spacetime around a perfectly spherical, non-rotating mass. He mailed the solution to Einstein from the front. Einstein wrote back, astonished, saying he had not expected an exact solution to emerge so quickly. Schwarzschild died months later from a disease contracted at the front. He never knew what his solution implied. Buried inside the mathematics was a critical value, a radius. For any given mass, there exists a specific threshold. Compress that mass below this radius, and the resulting curvature of spacetime becomes so extreme that not even light can escape. For our sun, that radius, now called the Schwarzschild radius, is approximately 3 kilometers. For the entire mass of the Earth, it is roughly 9 millimeters. The Earth compressed to the size of a marble. The sun compressed to a sphere smaller than a city intersection. At those densities, the equations predicted something that nearly every physicist of the era found either absurd or unsettling: a singularity, a boundary, a point of no return. Einstein spent years trying to argue it away. In a 1939 paper, he attempted to demonstrate that real physical matter could never actually collapse to within its Schwarzschild radius, that the orbital mechanics of infalling particles would prevent it. His reasoning was technically elegant and completely wrong. The error was not mathematical but physical. He had assumed idealized conditions that nature, it turned out, does not honor. When massive stars exhaust their nuclear fuel, the thermal pressure that counteracts gravity disappears. What follows is not an orderly retreat. It is a catastrophic, irreversible implosion. The physics of stellar collapse was clarified, with brutal precision, by J. Robert Oppenheimer and his student Hartland Snyder in a paper published in September 1939, the same month Germany invaded Poland. Their work showed that a sufficiently massive collapsing star would not halt. It would not stabilize into a neutron star or some exotic intermediate object. It would keep collapsing, indefinitely, until the Schwarzschild radius was breached, and the resulting object would be permanently and entirely cut off from the rest of the universe. An observer watching from a safe distance would see the collapsing star's light redshift and dim asymptotically, appearing to freeze at the boundary as gravitational time dilation stretched the light's travel time toward infinity. The star would seem to halt at the edge, but that image would be a distortion, a relic of how light behaves in extreme curvature. The collapse in the reference frame of the infalling matter would continue uninterrupted. That distinction between what a distant observer sees and what an infalling observer experiences is not a philosophical curiosity. It is the central, defining feature of black hole physics, and it is the source of the deepest, most stubborn confusion about what black holes actually are. What does a distant observer actually see? As an object approaches the event horizon of a black hole, the light it emits must climb out of an increasingly deep gravitational well to reach the observer. The energy of each photon decreases as it fights against gravity, shifting toward longer wavelengths, first from visible light to infrared, then to microwave, then to radio frequencies so long they carry almost no detectable energy at all. Simultaneously, the rate at which photons arrive at the observer slows down, because time itself is running slower near the horizon. The object appears to dim and redden, its image stretching and fading over an increasingly long period, approaching but never quite reaching the event horizon in the observer's frame of reference. From the outside, the infalling object appears to freeze. But in the reference frame of the object itself, or of any observer falling freely toward the horizon, nothing dramatic happens at the boundary. There is no wall, no flash of light, no physical jolt. General relativity predicts that for a sufficiently large black hole, where the tidal forces at the event horizon are mild enough, a freely falling observer would cross the boundary without any local, detectable signal. The curvature there is real, but spread across enough space that it would not immediately tear apart a compact object. The event horizon in the local frame is invisible. It is defined entirely by what the future holds, not by any present sensation. This is one of the most counterintuitive results in all of physics. The most consequential boundary in the known universe, the point past which time and causality themselves become one-directional dead ends, announces itself with complete silence. You would not know you had crossed it until it was, by definition, too late to communicate that fact to anyone outside. How long does the fall take? In the infalling observer's proper time, the time measured by a clock they carry, it is finite. For a stellar mass black hole with a mass 30 times that of our Sun and a Schwarzschild radius of roughly 88 kilometers, the freefall time from the event horizon to the central singularity is measured in microseconds. The object does not drift leisurely towards some dark center. It arrives almost instantaneously once the threshold is crossed. For a supermassive black hole the scale of Sagittarius A, with a Schwarzschild radius of approximately 12 million kilometers, the freefall time from horizon to singularity is on the order of tens of seconds. For something the mass of M87 Tyche, it would be measured in hours. The more massive the black hole, the gentler the horizon and the longer the interior journey. Yet the destination, in all cases, is the same. The singularity is not a place in space. This is the misconception that requires the sharpest correction. Inside the event horizon, the roles of space and time exchange. In normal space-time, you have freedom of movement in 3 spatial dimensions. You can go left or right, forward or backward, up or down. But you have no freedom in the time dimension. Time flows in one direction only, and you cannot reverse it. Inside the event horizon of a black hole, that structure inverts. The radial direction toward the singularity becomes time-like. It is not a location you can choose to avoid. It is the future. The singularity is not something sitting at a fixed point in space toward which you travel. It is something that lies ahead of you in time. It is when you are going, not where. No known force, no rocket engine, no imaginable material, no physical process of any kind can prevent an infalling observer from reaching it, because preventing it would require traveling backward in time. And the known laws of physics do not permit that. The singularity is the point at which those same laws, as currently formulated, cease to make any prediction at all. The mathematical objects that describe physical quantities, density, curvature, tidal force, diverge to infinity. In physics, when an equation returns infinity as an answer to a physical question, it is not telling you that something infinite is there. It is telling you that the theory has reached the limit of its domain. General relativity, for all its extraordinary precision and predictive power, is not the final word. It is an approximation, a description of how space-time behaves in the regime of large masses and large distances, derived without any reference to the quantum behavior of matter at the smallest scales. At the singularity, both regimes collide. Quantum mechanics and general relativity, the 2 foundational pillars of modern physics, meet head-on at a point of infinite density, and they produce an answer that neither theory can interpret. That collision has a name. Physicists call it the information paradox. And it is, by consensus, the most profound unresolved problem in theoretical physics today. The outline of the problem is this. Quantum mechanics is built on a principle called unitarity, which states that information is never destroyed. Every quantum state evolves according to equations that are, in principle, reversible. If you know the complete quantum state of a system at any moment, you can run the equations backward and recover the complete state at any earlier moment. Information, the precise record of how every particle in the universe is configured, is, in quantum mechanics, conserved absolutely. It cannot vanish. Black holes appear to violate this. Stephen Hawking demonstrated in 1974 that black holes are not entirely black. Quantum effects at the event horizon cause the black hole to radiate, slowly over astronomical timescales, emitting thermal radiation that carries energy away from the black hole and causes its mass to gradually decrease. This radiation, now called Hawking radiation, is, to an extraordinary approximation, perfectly random. It carries no information about what fell into the black hole. As the black hole radiates and shrinks over timescales so long they dwarf the current age of the universe, it eventually evaporates entirely. And if the radiation carries no information, then whatever fell in, every particle, every quantum state, every structured configuration of matter that crossed the horizon, is gone. Not redistributed, not encoded somewhere subtle, simply erased from the universe's ledger. Either quantum mechanics is wrong, or general relativity is wrong, or both require modifications so fundamental that they amount to a new theory of physics. As of today, no such theory exists in complete form. The event horizon is not just an edge in space. It is the place where the two greatest intellectual achievements in the history of science go to war with each other, and neither one wins. That confrontation is about to get significantly more violent. Gravity is geometry. Not a force transmitted between objects, not an invisible rope pulling masses together, but the shape of space-time itself, the curvature of the four-dimensional fabric in which every particle, every photon, every atom in the universe moves. This is the conceptual revolution that separates Newtonian gravity from Einsteinian gravity, and the distance between them is not a refinement. It is a complete reconstruction of physical reality from the foundations up. Newton's gravity worked extraordinarily well. For more than 2 centuries, his inverse square law described the motion of planets, the arc of cannonballs, the precession of equinoxes, and the return of comets with a precision that seemed, to most working scientists of the 18th and 19th centuries, essentially complete. The framework was simple. 2 masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. Apply the equation, get the answer. It was clean, predictive, and powerful. It was also fundamentally wrong about what gravity actually is. Newton himself knew something was missing. In his own writing, he admitted that the idea of a force acting instantaneously across empty space, with no medium, no mechanism, no carrier, was philosophically unsatisfying. He called it action at a distance, and described it as so great an absurdity that he believed no man who had a competent faculty of thinking could ever fall into it. He was right to be troubled. It took 230 years for the actual mechanism to be identified. Einstein's insight, arrived at through a decade of thought experiments, false starts, mathematical struggle, and one pivotal realization known as the happiest thought of his life, was that gravity and acceleration are locally indistinguishable. Stand in a closed room with no windows. If the room is sitting on the surface of the Earth, you feel your weight pressing you to the floor. If the room is in deep space, accelerating upward at 9.8 meters per second squared, you feel exactly the same thing. No local experiment you perform inside that room can distinguish between the two situations. They are physically identical. This is the equivalence principle, and it is the cornerstone on which general relativity is built. If gravity and acceleration are the same thing locally, then gravity cannot be a force in the Newtonian sense. Forces cause acceleration. If gravity is indistinguishable from acceleration, then objects in gravitational fields are not being accelerated by a force. They are following the straightest possible paths through a curved space-time. The Earth does not pull the Moon toward it. The mass of the Earth curves the space-time around it, and the Moon follows the straightest possible trajectory through that curved geometry. From a distance, that trajectory looks like an orbit, but locally, the Moon is in free fall, weightless, unaccelerated, moving in a straight line through bent space. This is not a metaphor, it is a precise mathematical statement. The paths that freely falling objects follow through curved spacetime are called geodesics, the generalization of straight lines to curved geometries. Light follows geodesics too. Every photon emitted anywhere in the universe travels along the straightest path available to it through whatever spacetime geometry it finds itself in. Near a massive object, that geometry is curved, and the photon's path curves with it. This is not light being deflected by gravity in the Newtonian sense. It is light doing exactly what light always does, traveling in a straight line through a space that is itself bent. The first observational confirmation of this came on May 29, 1919. During a total solar eclipse, the British astronomer Arthur Eddington led expeditions to the island of Príncipe off the west coast of Africa and to Sobral in northern Brazil to photograph stars near the edge of the sun's disk. The moon's shadow allowed the stars to be seen in daytime, and their apparent positions could be compared against their known positions when the sun was not nearby. Einstein's theory predicted that the sun's gravity would bend the light from background stars by 1.75 arcseconds, roughly half the apparent diameter of Jupiter as seen from Earth, and exactly twice what Newtonian gravity would predict. Eddington's measurements confirmed Einstein's value. The news reached the world's press within months and made Einstein overnight the most famous scientist alive. But Eddington's eclipse was a gentle curvature, a whisper. The bending of starlight by our sun represents a gravitational field so mild, so far from relativistic extremes, that the differences between Newton and Einstein amount to fractions of arcseconds and parts per million in orbital calculations. To see general relativity operating at full power, to see the geometry of spacetime pushed to its absolute limits, you need objects incomparably denser and more massive than any star in our neighborhood. You need the geometry inside and around a black hole. The mathematics describing that geometry is contained in Einstein's field equations, a set of 10 coupled, nonlinear partial differential equations relating the curvature of spacetime at every point to the distribution of mass and energy at that point. They are among the most complex equations in all of physics. The left side describes geometry, the shape of spacetime. The right side describes matter and energy. What is in that spacetime? The equations say, with compressed mathematical elegance, spacetime tells matter how to move, and matter tells spacetime how to curve. Far from a black hole, the geometry is mild. The Schwarzschild solution, the exact solution Schwarzschild derived in 1915, describes the spacetime geometry around any spherically symmetric, non-rotating, electrically neutral mass. At large distances, it reduces to exactly Newtonian gravity. The corrections are small. GPS satellites require relativistic corrections to their onboard clocks of approximately 38 microseconds per day. A combination of gravitational time dilation from being higher in Earth's gravitational field and kinematic time dilation from their orbital velocity. Without those corrections, GPS navigation would accumulate errors of roughly 11 kilometers per day. The relativistic effects are real, measurable, and consequential even at the mild curvatures of Earth's gravitational field. As you move inward toward a black hole, the corrections grow. They do not grow gently. They explode. The quantity that governs the strength of relativistic effects near a massive object is the ratio of the Schwarzschild radius to the actual radius of the object. For the Earth, this ratio is roughly 1 part in 700 million. Utterly negligible in almost every practical context. For the Sun, the ratio at its surface is approximately 4 parts per million, small but detectable. For a neutron star, the ultra-dense remnant of a collapsed star that narrowly avoided becoming a black hole, with a mass between 1 and 2 times that of our Sun compressed into a sphere approximately 20 kilometers across, the ratio approaches 1/10. Relativistic effects at the surface of a neutron star are not corrections. They are dominant features. Time runs measurably slower at the surface of a neutron star than at a safe distance. The escape velocity from the surface is a substantial fraction of the speed of light, on the order of half. At the event horizon of a black hole, the ratio reaches exactly 1. The Schwarzschild radius equals the actual radius. And at that point, the mathematics does something that has no analogy anywhere else in physics. The time component of the metric, the mathematical object that encodes how spacetime is measured, goes to 0. Proper time, the time measured by a clock in that region, does not slow down or nearly stop, it stops. The coefficient that converts coordinate time to physical time reaches 0 at the horizon, and the geometry of spacetime undergoes the exchange of roles described in Act 2. The radial direction becomes time-like, and time as an independent dimension ceases to function as it does everywhere else in the universe. This is what time stops at a black hole actually means. Not that clocks malfunction, not that some local physical process breaks down. The geometric structure of time itself, its role as the dimension along which cause precedes effect, along which entropy increases, along which the laws of physics evolve systems forward, that structure, at the event horizon, undergoes a categorical transformation. To understand what drives this, you need to follow the tidal forces. Tidal forces are the differences in gravitational acceleration across an extended object. The fact that the near side of the object is pulled more strongly than the far side producing a stretching effect along the radial direction and a compression effect perpendicular to it. On Earth, tidal forces from the moon are responsible for ocean tides. The oceans on the side of the Earth facing the moon are pulled slightly more strongly than the Earth's center, and the oceans on the far side are pulled slightly less, producing two tidal bulges simultaneously. The effect is gentle. The difference in gravitational acceleration between the near and far side of the Earth due to the moon is approximately 100,000th of a meter per second squared. Near a stellar mass black hole with a mass 30 times that of our Sun, at a distance of 1,000 kilometers from the singularity, still well outside the event horizon, the tidal force across a human-scale object approximately 2 meters in length would be measured in millions of times Earth's surface gravity. The stretching force along the radial direction would be enough to disaggregate matter at the atomic level. Physicists call this process spaghettification, a deliberately informal term for what is, in reality, a complete relativistic tidal disruption. The object does not merely deform. It is drawn out into an increasingly thin stream of particles flowing toward the singularity, the leading edge accelerating faster than the trailing edge, the entire structure elongated beyond any physical integrity. The mass determines everything about the character of this experience. For a stellar mass black hole, spaghettification begins well outside the event horizon. For a supermassive black hole of several billion solar masses, the tidal forces at the event horizon are, counterintuitively, far gentler, because the horizon is so much farther from the singularity. The tidal force scales inversely with the cube of the distance from the center of mass. For M87 Chi, the tidal force at the event horizon across a 2-meter object is smaller than the tidal force the moon exerts on the Earth's oceans. An extended object could cross the event horizon of M87 Chi without any immediately destructive local effect, but it cannot stop, and it cannot return. And ahead of it, in time rather than in space, the singularity waits, not as a destination that could be avoided with sufficient thrust, but as the inevitable end of every possible world line that crosses the horizon. In the geometry of space-time inside a black hole, all future directed paths, every trajectory that any particle, any photon, any conceivable physical system could follow, converge on the singularity. It is not a place you fall into. It is the moment you are falling toward. The equations have one more thing to say about the interior, something that was not understood until Roy Kerr solved Einstein's field equations for a rotating black hole in 1963. Real black holes rotate. Every object in the universe that forms from the gravitational collapse of matter carries angular momentum, the conserved rotational motion inherited from the original cloud of gas and dust. As the object collapses, conservation of angular momentum causes the rotation to increase dramatically, exactly as a spinning ice skater pulling in their arms spins faster. The resulting geometry is not the clean, spherically symmetric Schwarzschild solution. It is the Kerr metric, a vastly more complex solution describing a spacetime that is dragged around with the rotating mass, twisted into a vortex-like structure that physicists call frame dragging. Frame dragging is not a metaphor. Near a rapidly rotating black hole, space-time itself is set in motion. An object attempting to remain stationary relative to the distant stars, to simply hover in place without orbiting, finds that it cannot. The rotation of space-time around the black hole forces it to co-rotate, regardless of any thrust it applies in the opposite direction. The region where this effect becomes irresistible, where even light moving counter to the rotation cannot remain stationary, is called the ergosphere. It lies outside the event horizon. And within it, something remarkable becomes theoretically possible, a process first described by the British physicist Roger Penrose in 1969, which carries his name. The Penrose process allows energy to be extracted from a rotating black hole. An object entering the ergosphere can, under the right conditions, split into two parts, one falling into the black hole with negative energy relative to a distant observer, and one escaping to infinity with more energy than the original object brought in. The excess energy comes from the rotational energy of the black hole itself. The black hole slows slightly. The escaping fragment carries away more energy than was deposited. The law of conservation of energy is not violated. The black hole pays the difference. The maximum efficiency of energy extraction through the Penrose process for a maximally rotating black hole is approximately 20.7% of the rest mass energy of the infalling material. For comparison, nuclear fission, the process that powers nuclear reactors and atomic bombs, converts approximately 0.1% of rest mass to energy. The Penrose process is, in principle, more than 200 times more energetically efficient than nuclear fission. It is the most efficient energy extraction mechanism permitted by the known laws of physics. Nobody has directly observed it, but the jets of relativistic plasma ejected from the poles of active galactic nuclei, streams of matter accelerated to a significant fraction of the speed of light and extending for hundreds of thousands of light years, are consistent with energy extraction from rotating supermassive black holes. The rotational energy of a black hole, the mass of M87T, spinning near its maximum rate, exceeds the rest mass energy of millions of solar masses of material. Those jets are not anomalies. They are among the most energetic, sustained phenomena in the observable universe, and the engine driving them may be the geometry of rotating spacetime itself. The black hole does not simply consume. Under the right physical conditions, it powers the universe around it. And at the center of all of this, deeper than the ergosphere, deeper than the event horizon, past the point where time functions as time, sits the singularity, and a theory that cannot describe it. A gap in the map that has no edges, only a label that translates from the language of mathematics to this, unknown. That gap is about to be confronted directly. For most of the 20th century, black holes were mathematics. Elegant, internally consistent, theoretically unavoidable, but mathematics nonetheless. The universe was not obligated to produce them. General relativity demanded their existence if certain conditions were met. But whether those conditions were ever actually met in nature, whether stars truly collapsed past their Schwarzschild radii and produced genuine spacetime singularities surrounded by event horizons, remained an open and genuinely contested question among physicists well into the 1960s. The shift began not with a telescope, but with a radio receiver and an anomaly nobody could explain. In 1963, the astronomer Martin Schmidt was working at the Palomar Observatory in California, analyzing the optical spectrum of a peculiar object that had been cataloged as a radio source, a point-like source of intense radio emission that appeared in visible light photographs to resemble an ordinary faint blue star. The object's designation was 3C273. It had been identified in the third Cambridge Catalogue of Radio Sources as one of the brightest radio emitters in the sky, yet its optical counterpart was dimensionless. No extended structure, no surrounding nebulosity, nothing that resembled a galaxy or a cloud of gas. It looked, for all practical purposes, like a star. Schmidt stared at its spectrum for weeks. The emission lines, the bright spectral fingerprints produced by specific atoms radiating at known frequencies, were in entirely the wrong positions. They did not match hydrogen. They did not match helium. They did not match any element he could identify, and Schmidt was among the most skilled observational astronomers of his generation. Then, in February of 1963, the answer arrived with the particular clarity that characterizes genuinely transformative scientific insight. The lines were hydrogen. They were simply red-shifted, shifted toward longer wavelengths by a factor of 16%. A redshift of 16%, interpreted through Hubble's law relating redshift to distance, placed 3C273 at a distance of approximately 2 billion light-years. 2 billion. The object was not a star in the Milky Way. It was not even a nearby galaxy. It was a point-like source of radiation located 2 billion light-years away, and yet it was bright enough to be detected easily with mid-20th century radio and optical telescopes. The energy output required to explain that brightness at that distance was staggering, equivalent to the combined light of hundreds of entire galaxies, all emanating from a region so compact it was spatially unresolvable. A region likely no larger in astronomical terms than our solar system. Schmidt's paper announcing this result was published in Nature in March of 1963. Within months, similar objects were identified across the sky. They were named quasi-stellar objects, quasars. and their existence posed an energy problem so severe that it forced a complete rethinking of what kinds of physical processes the universe was actually capable of producing. The thermal nuclear fusion that powers stars, the process by which hydrogen is fused into helium, releasing energy at a rate governed by Einstein's mass-energy equivalence, converts approximately 0.7% of the rest mass of hydrogen fuel into energy. It is an extraordinarily efficient process by terrestrial standards, and it is what allows the sun to shine for 10 billion years. But it is nowhere near efficient enough to explain quasars. To produce the luminosity of a quasar through stellar fusion alone, you would need to be converting stellar fuel at a rate so enormous that the object would exhaust any plausible fuel supply in a cosmically negligible time. The only known mechanism capable of producing quasar luminosities from a compact region is gravitational accretion onto a supermassive black hole. Matter falling into a deep gravitational well releases gravitational potential energy. For matter falling toward a black hole, that energy release is governed by the depth of the potential well, and no potential well in the universe is deeper than the one surrounding a black hole. The efficiency of energy conversion through accretion depends on the geometry of the inspiral and on whether the black hole is rotating. But for a non-rotating black hole, the maximum efficiency is approximately 5.7% of the rest mass energy of the accreting material. For a maximally rotating Kerr black hole, it approaches 42%. Even the lower value is 8 times more efficient than nuclear fusion. A supermassive black hole of 1 billion solar masses, accreting matter at a rate of just a few solar masses per year, can produce a luminosity comparable to the entire observable output of a large galaxy. The energy comes not from destroying matter, but from releasing the gravitational potential energy of matter as it spirals inward through an accretion disk. A flattened, differentially rotating structure of superheated plasma surrounding the black hole, glowing across the electromagnetic spectrum from radio waves to X-rays, with temperatures in the inner regions reaching tens of millions of degrees. The identification of quasars as accreting supermassive black holes did not happen cleanly or quickly. It was the product of 2 decades of increasingly detailed observation, theoretical modeling, and a series of independent discoveries that converged on the same conclusion from different directions. The X-ray Observatory Uhuru, launched in 1970, detected powerful X-ray sources across the sky that had no obvious optical counterparts. Cygnus X1, one of the first and brightest, was identified in 1971 as a binary system, a stellar mass compact object locked in orbit with a blue supergiant companion star, accreting matter from the companion's stellar wind. The compact object's mass, inferred from the orbital dynamics of the binary system, exceeded the maximum mass theoretically possible for a neutron star. The community was cautious. The evidence was indirect. But the conclusion was almost inescapable. Cygnus X1 was a black hole. The caution was warranted. The history of astronomy is littered with premature identifications and confident claims later retracted. But the evidence accumulated, instrument by instrument, observation by observation, until the alternative explanations became untenable. The decisive turn in the search for the supermassive black hole at the center of our own galaxy came from a program of patient, systematic infrared observation that unfolded over more than 2 decades. The center of the Milky Way is invisible in optical wavelengths. The intervening dust and gas of the galactic plane absorb visible light almost completely, dimming the galactic center by a factor of roughly 1 trillion in visible frequencies. Infrared radiation penetrates that dust. Beginning in the early 1990s, 2 independent research groups, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, and one led by Andrea Ghez at the University of California, Los Angeles, began tracking the positions of stars in the dense stellar cluster at the galactic center, using adaptive optic systems that corrected in real time for the blurring effects of Earth's atmosphere. What they observed, over years and then decades of accumulated data, was extraordinary. The stars near the galactic center were not moving in the gentle, stately orbits characteristic of stars in the outer galaxy. They were moving fast, in some cases at velocities exceeding thousands of kilometers per second, and their orbits were tightly curved, in some cases completing full ellipses around a central point with periods of only a few years. The star designated S2, one of the most closely monitored in the cluster, has an orbital period of approximately 16 years and reaches a closest approach to the central object, called periapsis, of roughly 120 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers. S2 passes within 120 times that distance of something that cannot be seen directly. The orbital dynamics are unambiguous. The mass required to produce those stellar velocities and orbital geometries, concentrated within a volume no larger than our solar system, is approximately 4 million times the mass of our Sun. No known configuration of normal matter, no cluster of stars, no exotic gas cloud, no concentration of dark matter could fit that much mass into that small A volume without collapsing into a black hole. The object is Sagittarius A. And for this work, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics in 2020, the prize explicitly citing the discovery of a supermassive compact object at the center of our galaxy. Ghez became only the 4th woman in history to receive the Nobel Prize in Physics. The Nobel announcement came roughly 18 months after an event that had already shifted the entire conversation. On April 10, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, specifically the supermassive black hole M87 Twax at the center of the Messier 87 galaxy, 55 million light-years away. The image showed a bright, asymmetric ring of emission surrounding a dark central region, the shadow cast by the event horizon against the glowing backdrop of the accretion disk. The asymmetry of the ring, brighter on one side than the other, is consistent with relativistic beaming. The plasma on the side of the disk rotating toward the observer is Doppler boosted to higher apparent brightness, while the side rotating away is dimmer. This is not a theoretical prediction being tested for the first time. It is a direct observational consequence of special relativity, visible in the image itself. The Event Horizon Telescope is not a single instrument. It is a global network of radio observatories spanning 4 continents, operating simultaneously and recording data on hard drives that are physically shipped to central processing facilities and correlated using a technique called very long baseline interferometry. The effective aperture of the array is approximately equal to the diameter of the Earth. The angular resolution achieved is equivalent to reading the date on a coin in New York from a distance of Los Angeles, roughly 4,000 kilometers. It is the highest angular resolution ever achieved in the history of observational astronomy. In 2022, the same collaboration released an image of Sagittarius A, the black hole at the center of our own galaxy. Imaging it was technically more difficult than imaging M87 Twax, despite Sagittarius A being vastly closer because the gas and plasma near it orbit so rapidly, completing full circuits in minutes rather than days, that the structure of the emission changed significantly during each night of observation. The collaboration developed new imaging algorithms specifically to account for this variability. The result was a ring of emission strikingly similar in overall morphology to the M87 Tau image, confirming that the same fundamental physics governs both objects across a mass range of more than 3 orders of magnitude. 2 black holes, 2 completely different scales, the same geometry, the same ring, the same shadow. General relativity had predicted the structure of that shadow with complete precision before a single pixel of either image was captured. The radius of the shadow, the angular size of the dark region at center, is determined by the photon sphere, the radius at which photons orbit the black hole in unstable circular orbits. For a non-rotating black hole, this radius is exactly 1.5 times the Schwarzschild radius. Photons arriving from infinity at exactly this impact parameter neither escape to infinity nor fall into the black hole. They orbit indefinitely, in principle, until perturbed. The photon sphere is the knife edge between capture and escape, and its angular size, as seen by a distant observer, defines the edge of the shadow. The theoretical prediction and the observed shadow size agreed to within the measurement uncertainties. The universe did not have to work this way. The shadow could have been larger or smaller. The ring could have been absent. The plasma distribution could have produced an image inconsistent with the predictions of general relativity. None of those things happened. What appeared on the screen of every observatory on Earth on April 10, 2019, was exactly what Einstein's equations, written in 1915 in Berlin, said it would look like. 1 century, 0 adjustments required. The black hole had stopped being a solution to an equation. It had become a face. And behind that face, past the luminous ring, past the shadow boundary, past the event horizon that no photon in that image could have crossed and returned from, the information paradox still waited, unresolved, deepening, pulling at the foundations of physics with the same patient, irresistible force that pulls everything else. The image answered one question with absolute finality. It opened 3 more that may take another century to close. Stephen Hawking was 32 years old when he discovered that black holes die. The year was 1974. Hawking was already living with the progressive motor neuron disease that would eventually confine him entirely to a wheelchair and strip him of his voice. But his mathematical faculties were operating at a level that few physicists in history have matched. He had spent the preceding years developing the formal mathematical framework for black hole thermodynamics, a field that had emerged almost accidentally from a collision between general relativity and a branch of physics that, on first encounter, seems to have no business interacting with it at all. The collision began with Jacob Bekenstein, a graduate student working under John Wheeler at Princeton in the early 1970s. Bekenstein noticed something deeply uncomfortable about black holes from the perspective of thermodynamics. The second law of thermodynamics states that the total entropy of a closed system, the measure of disorder, of the number of possible microscopic configurations consistent with the macroscopic state of the system, never decreases. It can stay the same. It can increase. It cannot go down. This law is not a suggestion. It is among the most robustly tested statements in all of physics, and its violation would constitute a crisis of the first order. Black holes appeared to violate it. If you throw a cup of hot gas, a highly ordered low-entropy system, into a black hole, the black hole's external appearance changes only in its mass, charge, and spin. Everything else about it remains identical. The information about the entropy of the gas, its internal configuration, its thermodynamic state, all of it disappears behind the horizon. From the outside, the entropy of the observable universe appears to have decreased. The second law appears broken. Bekenstein's resolution was audacious. He proposed that black holes themselves carry entropy, that the event horizon is not a featureless boundary, but a thermodynamic surface with a well-defined entropy proportional to its area. Specifically, he proposed that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck length squared. The Planck length being the fundamental quantum scale of spacetime, approximately 1.6 times 10 to the power of negative 35 meters. This is unimaginably small. Placed end to end, it would take approximately 10 to the power of 20 of these lengths to span the diameter of a single proton. The area of the event horizon of Sagittarius A, the 4 million solar mass black hole at the center of our galaxy, measured in Planck length squared, is a number so large it has no name in common use. The entropy of that black hole, in natural units, exceeds the entropy of every star, every planet, every atom of ordinary matter in the entire observable Milky Way galaxy combined, by an enormous margin. Black holes are not just the densest objects in the universe, they are the most entropic. They are the endpoints toward which entropy, over cosmological timescales, is relentlessly and inevitably flowing. Hawking's initial reaction to Bekenstein's proposal was skepticism, bordering on hostility. His objection was thermodynamic and precise. If a black hole has entropy, it must have temperature. If it has temperature above absolute zero, it must radiate. But nothing can escape from a black hole. The radiation was impossible. The argument appeared to refute Bekenstein by reductio ad absurdum. Then Hawking did the calculation. He applied the formalism of quantum field theory, the framework describing how quantum particles behave in curved spacetime, to the region near the event horizon. What he found contradicted his own objection completely. The quantum vacuum near the event horizon is not empty. In quantum field theory, the vacuum is a roiling sea of virtual particle pairs, particle and antiparticle flickering into and out of existence on timescales governed by Heisenberg's uncertainty principle. too brief to be observed directly, but producing measurable effects on the energy levels of atoms and the behavior of electromagnetic fields. Near the event horizon, the intense space-time curvature can separate a virtual pair before the partners annihilate each other. One partner falls across the horizon, the other escapes to infinity. To a distant observer, the escaping particle appears as real radiation, thermal radiation, with a temperature determined by the surface gravity of the black hole. The black hole radiates, it loses mass. Slowly, almost imperceptibly slowly for any black hole of astrophysical size, but continuously and irreversibly. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. For a stellar mass black hole of 10 solar masses, the Hawking temperature is approximately 6 billionths of a Kelvin, 6 billionths of a degree above absolute zero. The cosmic microwave background radiation, the thermal afterglow of the Big Bang permeating all of space, has a temperature of approximately 2.7 Kelvin. The black hole is absorbing vastly more energy from the cosmic microwave background than it is radiating through Hawking radiation. It is effectively growing, not shrinking. It will continue to grow until the universe has expanded and cooled enough that the cosmic microwave background temperature drops below the Hawking temperature of the black hole. For a 10 solar mass black hole, that will not happen for an astronomically remote future time, on the order of 10 to the power of 67 years. The current age of the universe is approximately 1.4 times 10 to the power of 10 years. The numbers involved in black hole evaporation operate on timescales that make the current age of the universe look like a rounding error. For a black hole of 1 solar mass, the complete evaporation time, from its current mass to zero, is approximately 2 times 10 to the power of 74 years. Written out, that is a 2 followed by 74 zeros. For Sagittarius A, with 4 million solar masses, the evaporation time scales as the cube of the mass, and the result is a number so remote in time that it belongs to a category of future epochs that has no observational anchor whatsoever. The universe as it currently exists, with stars, galaxies, planetary systems, chemistry, and biology, will be a memory so ancient as to be effectively inaccessible long before the first astrophysical black hole completes its evaporation. In that remote future epoch, as a black hole approaches its final moments, something changes. The evaporation accelerates. As mass decreases, the Hawking temperature increases. Inversely proportional to mass, the temperature climbs as the mass falls, producing a feedback that becomes self-reinforcing. The final stages of black hole evaporation are not a slow fade. They are a burst. The last fraction of a second of a black hole's life, as its remaining mass approaches the Planck mass, approximately 2.2 times 10 to the power of -8 kilograms, roughly the mass of a flea's egg, releases energy in a final explosive emission of high-energy gamma radiation. The black hole does not quietly disappear. It ends in a flash. No such event has ever been observed. The small primordial black holes that might have formed in the dense, turbulent conditions of the early universe, if they exist, could be completing their evaporation now or in the recent cosmological past. Searches for the gamma-ray signatures of evaporating primordial black holes have been conducted using space-based gamma-ray observatories, including the Fermi Gamma-Ray Space Telescope. No confirmed detection has been made. Their absence constrains but does not eliminate models of primordial black hole formation in the early universe, and the search continues. The final evaporation is where the information paradox reaches its sharpest edge. Throughout the evaporation process, the Hawking radiation emitted by the black hole is, to a very high approximation, thermal, random, featureless, carrying no information about the specific quantum states of the matter that originally fell in. If the evaporation is complete and the radiation is truly thermal all the way to the end, then the information is gone. The quantum state of every particle that ever fell into the black hole, every electron spin, every photon polarization, every quark color charge, the complete quantum description of everything from the gas clouds that formed the original star to any matter that subsequently fell in, has been permanently erased from the universe. Unitarity is violated. The laws of quantum mechanics are broken. This is not a small problem. It is not a technical detail awaiting a straightforward fix. It is a foundational contradiction between the two most successful physical theories in human history, and it has occupied some of the best theoretical minds in physics for more than 50 years without resolution. The candidate solutions are numerous, and each carries radical implications. One class of proposals suggests that the information is encoded in the Hawking radiation in subtle, non-thermal correlations. That the radiation is not perfectly thermal, but carries quantum imprints of the infallen matter in correlations between photons emitted at different times, correlations so delicate they approach the theoretical limits of quantum information encoding. This is consistent with unitarity and does not require modifying general relativity, but it requires that the evaporation process be non-local in a way that is deeply difficult to reconcile with the causal structure of spacetime near the horizon. A second class of proposals invokes the concept of black hole complementarity, developed in the 1990s by Leonard Susskind, Laris Thorlacius, and John Uglum. Complementarity proposes that the descriptions of events as seen by an infalling observer and a distant observer are both valid but mutually exclusive, that no single observer can ever access both descriptions simultaneously, and therefore no contradiction actually exists. The infalling observer sees information falling normally through the horizon. The distant observer sees information encoded in Hawking radiation. Both descriptions are correct within their respective observational domains. The paradox in this view is not a physical contradiction but a category error, an attempt to combine two irreconcilable perspectives into a single narrative that no observer can ever actually construct. A third and more recent proposal, emerging from work by Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully in 2012, collectively known as the AMPS firewall argument, concluded that complementarity itself is internally inconsistent. Their argument showed that preserving unitarity, while also requiring that infalling observers experience nothing unusual at the horizon, leads to a direct contradiction with the monogamy of quantum entanglement. The resolution they proposed was radical. The event horizon is not the smooth, locally unremarkable boundary predicted by classical general relativity. It is a firewall, a region of enormously energetic radiation that destroys any infalling observer at the moment of crossing. The equivalence principle, the cornerstone of general relativity, breaks down precisely at the horizon. If the firewall argument is correct, then one of the foundational assumptions of general relativity fails at the event horizon of every black hole in the universe. The freely falling observer does not cross unperturbed into the interior. They are incinerated at the boundary by a wall of Planck-scale energy.
The interior of the black hole, the region past the horizon, the direction of the singularity, the inverted time-like dimension, may not exist at all in any physically meaningful sense. The debate ignited by the AMPS paper has not been resolved.
It has deepened, branching into proposals involving the holographic principle, the ADS-CFT correspondence, and the relationship between quantum entanglement and spacetime geometry itself, a direction formalized in the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. Their proposal connects two seemingly unrelated phenomena: Einstein-Rosen bridges, the wormhole solutions to general relativity connecting distant regions of spacetime, and Einstein-Podolsky-Rosen pairs, the entangled quantum systems whose correlations are the basis of quantum information theory. Maldacena and Susskind proposed that entanglement and wormholes are not merely analogous. They are the same thing, expressed in different physical languages. Quantum entanglement between two particles is, in this view, a microscopic wormhole connecting them through spacetime. If this is correct, then spacetime itself, the smooth, continuous geometric fabric described by general relativity, is not fundamental. It is emergent. It is woven from the quantum entanglement structure of underlying degrees of freedom that general relativity cannot see. The black hole in this picture is not a defect or an anomaly in spacetime. It is a region where the entanglement structure of the quantum vacuum is so intense that spacetime, as a geometric concept, reaches its limits of validity and begins to dissolve back into the quantum substrate from which it arose. The singularity, in this view, is not a place of infinite density. It is the boundary of the geometric description itself, the point at which spacetime, as a language for describing physical reality, runs out of words. That boundary is not the end of physics. It is the beginning of a deeper layer, one that current theory can gesture toward but not yet describe, one that will require a synthesis of quantum mechanics and gravity more complete and more fundamental than anything yet written. The equations that describe it do not yet exist in final form. The physicists who will write them may not yet have been born. The universe built these objects before we had the mathematics to understand them. It has been waiting, patient and indifferent, for us to catch up. Every atom in the human body was forged inside a star. This is not poetry. It is nucleosynthesis, the well-documented, experimentally confirmed process by which the nuclear furnaces of massive stars build progressively heavier elements from hydrogen and helium over millions of years of sustained fusion. The carbon in every cell, the oxygen in every breath, the iron carrying oxygen through every bloodstream right now. Each of those atoms was produced inside a stellar interior, expelled into space when the star died, and eventually incorporated into the molecular cloud that collapsed to form our solar system 4.6 billion years ago. The atoms have histories that predate the Earth by billions of years. They have been part of other stars, other clouds, other chemical arrangements entirely before arriving in their current configuration. The stars that made those atoms are gone. Most of them died violently, in supernova explosions that briefly outshone entire galaxies, scattering their enriched outer layers across light years of space while their cores collapsed inward. Some of those cores became neutron stars. Some crossed the threshold and became black holes. The black hole is not the antithesis of life. It is, in a very direct physical sense, part of the same stellar cycle that made life chemically possible. The death that produces a black hole is the same category of death that seeds the interstellar medium with the heavy elements required for rocky planets, liquid water, and organic chemistry. The universe is not a static backdrop against which events occur. It is a system of processes, of matter cycling through phases of condensation, ignition, fusion, explosion, and collapse, over timescales so long that the entirety of recorded human history occupies a fraction too small to name meaningfully. The black hole is not an anomaly in this system. It is one of its endpoints. One of the forms that matter and energy take when gravity has had enough time and enough mass to do what gravity, without opposition, always does. What makes black holes singular, in the colloquial sense, not the mathematical one, is not their violence or their scale. It is what they reveal about the nature of the physical laws governing all of it. Every other object in the universe, no matter how extreme, can be described by physics that remains internally consistent. Neutron stars are dense beyond any terrestrial analog, but the equations describing them, though challenging, produce finite, interpretable answers. White dwarfs, magnetars, pulsars, gamma-ray bursters, all of them extreme, all of them describable. Black holes are the only objects in the known universe where the equations break, where the map runs out, where the most sophisticated theoretical framework humanity has ever constructed raises its hands and returns an undefined result. That breakdown is information. It is the universe pointing at something real, a regime of physics that exists, that operates, that has consequences for the structure of space-time and the fate of matter and energy, but that our current conceptual vocabulary is insufficient to describe. The singularity is not evidence that physics fails. It is evidence that physics is incomplete. There is a difference, and it is the difference between a dead end and an open door. The history of physics is, in large part, the history of confronting exactly these moments. Newtonian mechanics was extraordinarily successful until it encountered phenomena at high velocities and extreme gravitational fields, where its predictions diverged from observation. The divergence was not evidence that physics was broken. It was evidence that Newtonian mechanics was an approximation, a valid, powerful, extraordinarily useful approximation in its domain, but an approximation nonetheless. General relativity resolved that divergence and extended the domain of valid description by an enormous margin. Quantum mechanics resolved the divergence between classical physics and the behavior of matter at atomic and subatomic scales, extending the domain further still. Each extension required abandoning assumptions so deeply embedded in the previous framework that they had seemed self-evident. the absolute nature of time, the continuity of energy, the deterministic evolution of physical systems. The next extension will require abandoning something equally deeply embedded. Physicists do not yet know exactly what. The candidates include the smoothness of spacetime at the Planck scale, the strict locality of physical interactions, the fundamentality of spacetime geometry itself, and possibly the independence of the observer from the observed, a boundary that quantum mechanics has already blurred significantly. Whatever assumption must be released, the clues pointing toward it are concentrated most densely in the physics of black holes. The event horizon is not just a boundary in space. It is the boundary of the current theory, the place where the next layer of physical reality becomes unavoidable. Roger Penrose, who shared the Nobel Prize in Physics in 2020 for his mathematical proof that singularities are a generic feature of general relativity, not special cases, not artifacts of idealized symmetry, but inevitable consequences of gravitational collapse under very general conditions, has spent decades developing a cosmological framework called conformal cyclic cosmology. In this model, the universe undergoes an infinite sequence of aeons, each beginning with something equivalent to a Big Bang and ending in a state of maximum entropy dominated by black holes, which eventually evaporate through Hawking radiation until nothing remains but a cold, expanding sea of photons and gravitational waves. That final state, Penrose argues, is conformally equivalent to a new Big Bang. The geometry of the far future maps smoothly onto the geometry of a new beginning, and the cycle repeats. The evidence Penrose and his collaborators have cited for this model consists of anomalous concentric ring patterns in the cosmic microwave background. Patterns, they argue, are the imprints of black hole merger events from a previous aeon, whose gravitational wave signatures survived the conformal transition and left faint but detectable marks on the temperature map of our own universe's earliest moments. The claim is deeply controversial. Other analyses of the same data have reached opposite conclusions. The debate is ongoing, and the observational evidence remains genuinely ambiguous. But the framework itself represents something significant. A serious, mathematically rigorous attempt to address not just what black holes are, but what role they play in the largest scale structure of time itself, whether the universe has a direction, a cycle, or neither. The cosmic microwave background, that faint thermal radiation at 2.7 Kelvin permeating every cubic centimeter of space in the observable universe, is itself a kind of record. It was released approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, making the plasma that had filled all of space suddenly transparent to radiation. Before that moment, the universe was opaque. No photon could travel freely. The cosmic microwave background is the oldest light we can directly observe, a snapshot of the universe at an age of 380,000 years, stretched and cooled by 13.8 billion years of cosmic expansion into the microwave frequencies we detect today. It is a horizon. Not an event horizon in the black hole sense, but a causal horizon, the boundary of what can, even in principle, be observed from our location in space-time. Beyond it, in the temporal direction, lies the first 380,000 years of the universe's existence, inaccessible to electromagnetic observation forever. Gravitational wave observatories, LIGO, Virgo, and the future space-based LISA array can in principle probe earlier epochs, since gravitational waves were not blocked by the opaque plasma the way electromagnetic radiation was. The gravitational wave background from the earliest moments of the universe, including any signal from the inflationary epoch, is a frontier of active observational cosmology. It has not yet been directly detected, but it is being searched for. Black holes produce gravitational waves. The first direct detection of gravitational waves, announced by the LIGO collaboration on February 11, 2016, came from the merger of two black holes, one of approximately 36 solar masses and one of approximately 29 solar masses, located approximately 1.3 billion light-years away. The event, designated GW150914, released energy equivalent to approximately 3 solar masses, converted entirely to gravitational radiation in a fraction of a second. The peak gravitational wave power emitted during the final merger was approximately 50 times greater than the combined electromagnetic luminosity of every star in the observable universe at that moment. The signal that reached Earth, after traveling 1.3 billion light-years through expanding space, displaced the mirrors of the LIGO interferometers by a distance of approximately 1,000th the diameter of a proton. The interferometer arms are 4 kilometers long. The displacement was 1,000th of a proton diameter across 4 kilometers. It was the smallest displacement ever directly measured by any instrument in the history of human technology. And it was unambiguous. The waveform matched the predictions of general relativity for a binary black hole in spiral and merger with a precision that left no room for alternative interpretation. 2 black holes, orbiting each other with increasing speed as gravitational wave emission drained their orbital energy, spiraling inward over billions of years, finally merging in a fraction of a second, and the mathematics written in 1915 predicted the exact shape of the sound that event made in the fabric of spacetime, down to the detailed oscillatory ringdown as the merged remnant settled into its final Kerr geometry. The signal was called a chirp, a rising frequency sweep that lasted approximately 0.2 of a second in the sensitive frequency band of the detector. Researchers converted it to audio and played it. It was exactly the sound the equations said it would be. Since GW150914, the LIGO-Virgo-Cagra network has detected more than 90 gravitational wave events from compact binary mergers, including black hole mergers, neutron-star mergers, and mixed black hole-neutron-star mergers. Each event is a direct measurement of the spacetime geometry produced by the most extreme gravitational sources in the universe. Each waveform is a test of general relativity in the strong field, highly dynamic regime, the regime farthest from the gentle, nearly static conditions of the solar system where general relativity was first tested. Every event has confirmed the predictions. Not approximately, precisely. The theory has now been tested across an extraordinary range of scales and conditions, from the bending of light by the sun measured in Eddington's eclipse of 1919, to the orbital decay of the Hulse-Taylor binary pulsar measured over decades, to the shadow of a 6.5 billion solar mass black hole 55 million light-years away, to the gravitational wave chirp of 2 merging black holes 1.3 billion light-years distant. The physical regime spans more than 20 orders of magnitude in gravitational field strength. The agreement between theory and observation has held across all of it. And still, at the center, the singularity waits. It waits not as a threat or a mystery to be feared, but as a fact about the universe, a feature of reality that exists regardless of whether any mind is present to contemplate it. Somewhere between 10 and 100 million black holes of stellar mass are estimated to exist within the Milky Way alone. The nearest known stellar mass black hole candidate lies approximately 1,000 light-years away in the constellation Telescopium. 1,000 light-years is approximately 9.5 quadrillion kilometers. It is close enough on the scale of the galaxy to be considered a neighbor, and yet so far that the fastest spacecraft humanity has ever launched would take approximately 37 million years to reach it. We are surrounded by them. The supermassive black hole at the center of our galaxy sits 26,000 light-years away, anchoring the rotation of 200 billion stars with the gravitational influence of 4 million solar masses. It has been there in some form for most of the galaxy's history. It shaped the structure of the Milky Way's central bulge. Its past activity, evidence of which survives in enormous structures of hot plasma called the Fermi bubbles, extending approximately 25,000 light-years above and below the galactic plane, altered the distribution of gas and star formation across the inner galaxy for millions of years. The black hole did not wait for us to discover it. It was here first, by billions of years. The atoms that eventually became the first humans to look up at the night sky and wonder about the light they were seeing had, at some earlier point in their journey through the galaxy, been subject to the same gravitational geometry that governs everything within 26,000 light-years of that central mass. The black hole was not a discovery in the sense of something that was made by being found. It was a revelation, a feature of the pre-existing structure of things, uncovered gradually by instruments sensitive enough to detect its effects across distances the mind was not built to hold. Physics has a long tradition of this kind of revelation, of discovering that the universe operates according to principles far stranger, far more intricate, and far more beautiful than any prior framework suggested. Each time, the strangeness has proven to be not an obstacle, but an invitation. The quantum revolution began when the equations describing blackbody radiation returned an answer that contradicted every classical intuition, and following that contradiction to its conclusion, produced an entirely new framework for understanding matter and energy at the smallest scales. The relativistic revolution began when the equations of electromagnetism proved incompatible with the assumption of absolute time, and following that incompatibility to its conclusion, produced an entirely new framework for understanding space, time, and gravity. The information paradox is that kind of contradiction. The firewall argument is that kind of incompatibility. The singularity is that kind of undefined result. They are not failures. They are the edges of the map, the places where the current description of reality reaches its limit, and the next description begins. What lies beyond that limit cannot be said with confidence. The mathematics that will eventually describe it does not yet exist in complete form, but the direction is clear. The convergence of quantum mechanics and general relativity, of information theory and space-time geometry, of the physics of the very small and the physics of the very massive, this convergence is not a crisis. It is the next question. And the next question has always, in the history of physics, been more interesting than the last answer. The universe is approximately 13.8 billion years old. Modern astronomy, in the form recognizable to contemporary science, is approximately 400 years old. The general theory of relativity is 110 years old. The first image of a black hole is 6 years old. The first detection of gravitational waves is 9 years old. By any measure of the timeline available, we are not at the end of this story. We are, in the most precise scientific sense of the phrase, just beginning to see.